Every single day, we generate over 500 million tweets, send billions of emails, and record millions of sensor readings worldwide. But accumulating terabytes of raw data is not the same thing as possessing insight. The core challenge of modern management is having to choose a specific course of action from thousands of alternatives, often while operating under massive uncertainty. To convert that raw data into an actual competitive advantage, organizations must move along a mathematical maturity spectrum, transitioning from describing the past to automating the underlying decision-making process. Having data is not a strategy. Knowing how to extract foresight from it is the defining competitive advantage of the modern enterprise. We map this transition using the spectrum of business analytics. We plot the degree of complexity against the resulting competitive advantage. There are 3 tiers of mathematical maturity: descriptive, predictive, and prescriptive. Ascending this graph toward optimization is the strategic mandate for modern analysts. The first tier is descriptive analytics. Its sole function is to look backward and answer a single question: what happened? This involves historical data queries, dashboards, and basic structured database reporting. Traditional databases handle standard reports, but collapse under big data. We use the 4 V's framework. Volume is massive terabyte-scale storage. Velocity is real-time streaming speed. Variety means unstructured multimedia formats. Veracity accounts for uncertainty and missing values. Managing these 4 constraints requires completely new distributed processing architectures, like Hadoop, which divide massive workloads across large clusters of computers. Establishing this distributed infrastructure provides the computational capacity required to move past hindsight and begin forecasting. That brings us to the second tier, predictive analytics. Here, the focus shifts from the past to the future by utilizing historical patterns to estimate upcoming events. This tier relies on mathematical mechanisms like linear regression, time series forecasting, and Monte Carlo risk simulations. A classic forecasting task at this level requires an analyst to collect a sample of real historical data, apply a predictive model, and estimate the values of distinct future periods. We can see this in practice with the retail grocery chain Kroger. Kroger applies predictive data mining to years of loyalty card shopping data. By analyzing past behavior, they model specific household interests and target direct mailers tailored directly to those preferences. With 11 million mailers sent quarterly, this precision yields a 70% redemption rate, translating to an estimated $10 billion in annual coupon revenue. The apex of the maturity model is Tier 3, prescriptive analytics. Unlike the previous tiers, this level outputs a direct decision or course of action. A predictive forecast is just a number, but when you combine that forecast with a defined rule or optimization algorithm, it becomes a prescriptive, automated system. General Electric's use of the Internet of Things is the ultimate embodiment of a prescriptive system. Every day, GE parses nearly 50 million pieces of data from 10 million sensors installed across its global fleet of aircraft engines. The system analyzes sensor data to provide pilots with specific flying parameters, optimizing fuel efficiency and limiting unplanned downtime. Prescriptive analytics represents the operational endgame. It completely removes human guesswork and automates complex decisions to maximize competitive advantage. There are hidden costs to the maturity model. Operating at maximum analytical complexity introduces maximum legal and ethical risk. High-value analytics, especially prescriptive algorithms, require highly localized, highly personal user data. This creates a massive security liability. Consider the Disney Magic Band, an ecosystem designed to track localized, real-time user movement and preference data throughout a crowded theme park. Tracking humans at this scale necessitates severe legal guardrails. Strict compliance frameworks like the GDPR are mandatory, and failing to protect this data carries an average breach cost of $3.86 million. An organization's analytical capabilities are strictly capped by the strength of the security infrastructure protecting its raw data. There is also an ethical paradox built into these algorithms. Even if a system is driven by pure, objective mathematics, it can still generate biased, unethical, or destructive outcomes. One common flaw is proxy variable bias in predictive models. For example, a credit risk algorithm might use an innocuous input like a home zip code, which secretly acts as a proxy for an unethical variable like ethnicity. We also see unintended optimization consequences in machine learning. A recommendation engine might flawlessly execute its mathematical objective, like maximizing a user's total watch time. But to achieve that goal, it can inadvertently promote extreme content or conspiracy theories, simply because they keep users engaged. We have traced the path from structuring big data to forecasting the future to automating the enterprise. Ultimately, sustainable strategy relies on the rigorous alignment of data processing and mathematical forecasting with ethical human oversight.